So this is another place where you might find CO2 every day at work or maybe even at home in the kitchen. We use it in fire extinguishers. Now, if we shake this bottle, we can hear that there's some liquid slopping around inside, and that's liquefied CO2. So CO2 is useful as an extinguisher for fires because it doesn't sustain combustion. It's non-flammable. So if there is a fire, we squirt CO2, which is quite dense. It blankets over the fire, excludes oxygen and puts the fire out. So let's see some more gaseous CO2.
Carbon dioxide is a really interesting molecule. It's very simple. It has carbon here with 2 oxygen atoms, 1 on each side. So it's just 3 atoms in a row.
Today, what we're going to do is we're going to explore the 3 states of matter looking at a single molecule, and we're going to use CO2. So at standard temperature and pressure, CO2 is a gas. And actually, I'm breathing it out. So here we go. We'll make some CO2.
The molecule has many interesting properties. One of them is that most gases, when you compress them, will liquefy and form a liquid. And then if you cool the liquid down, it will freeze. What is interesting about carbon dioxide is that you cannot get the liquid at atmospheric pressure. So you can get all sorts of little containers that contain liquid CO2, but if you open them, release the pressure, the CO2 converts into a solid, so-called dry ice, which is very cold, but goes straight from the solid to the gas without melting.
So hopefully today we're going to look at CO2 as a gas, CO2 as a liquid, and CO2 as a solid, and perhaps we'll look at some reactions as well.
There are double bonds between the carbon and the oxygen, because each oxygen normally wants to be bonded to 2 atoms, but here you can see it's only bonded to 1 carbon, so it has a double bond, 2 bonds together.
So this is where we're going to get our CO2 from. It's a rather large cylinder. So on the cylinder, we have a device called a regulator, which you can see here. Now what that does is it limits the pressure of the gas that we get out into our pipe. So this is really for safety, because the pressure inside the cylinder is a lot higher than the pressure that we require in our reaction or inside our balloon. So here we have a balloon, a rather strange balloon. So now you can see we've collected a balloon full of carbon dioxide. And as you can see, it's a rather nice balloon. It's the same as any other balloon. What do you say about a balloon of CO2? So, CO2 is a gas.
CO2 is one of my favourite molecules because CO2 as a liquid or a highly compressed gas will dissolve chemicals just in the same way as petrol or other organic liquids will dissolve them. And so you can use carbon dioxide as a solvent for chemical reactions. And this highly compressed gas, the so-called supercritical fluid, is something that both I and Pete Licence, who does lots of our demonstrations, we've done a lot of research on this.
Most people, when they think of CO2, they think of it as a gas. But if you take that gas and you pressurise that gas, so you squeeze it, if you put it into a bottle perhaps or a container and you squeeze it, the gas molecules are brought closer and closer and closer and closer together until eventually they will condense and form a liquid phase. Now what we've done with our experiment is we've taken the CO2 and we've connected it to a special piece of apparatus, which you can see is made out of things like stainless steel and technical instrumentation. But the key thing about this apparatus is that unlike a normal stainless steel vessel, we have a window inside this vessel which is able to maintain pressure. It's able to take the stresses because of the pressure trying to push against the atmosphere.
And it's really good for chemical reactions. And again, by using carbon dioxide as a solvent, you can avoid having to use products made from petroleum, which might otherwise use up and deplete the petroleum. Whereas carbon dioxide, we have more than we know what to do with from various industrial processes, so it is available really quite widely.
So the window that you're looking through in this experiment is sapphire.
That must be expensive.
Hell yeah, they're about... The front window in this cell is approximately £800, and the rear window, the one which moves, is about £1,400. So quite expensive, and but absolutely critical for this experiment.
And if, as is proposed, CO2 is captured from power stations, there's going to be a huge amount of CO2, and if you can use that for chemical reactions, for extracting materials. One of the main commercial applications of high-pressure carbon dioxide at the moment is for decaffeinating coffee. Many years ago, coffee was decaffeinated using dry cleaning fluids, which can leave all sorts of residues in the coffee beans. People may not want to drink the coffee. But caffeine is soluble in CO2, and most of the other components of coffee beans are not. So you can extract the caffeine from green coffee beans, so you get decaffeinated coffee, and the CO2 leaves no residues at all. And then by reducing the pressure or washing the CO2 with water, you can get the caffeine out, and you can sell it to people to put in their soft drinks.
Now, Neil's been really active, and he's ordered in a special piece of CO2 for us, which he's going to get out of the box now. So what we thought we'd do today is perhaps a little bit of ice sculpting. So we're going to cut the CO2 in half and make a reaction vessel, okay? And then we're going to do a nice chemical reaction with it. So here, Neil's cutting the CO2 now with a saw, and this is the typical saw that you might find in a hardware shop or a do-it-yourself shop. So one of the advantages of sawing this material is that you don't have to clean up the sawdust, because it just evaporates.